Think about every single modern device you own. From the smartwatch on your wrist to the laptop on your desk, they all rely on our ability to control entirely invisible forces. Welcome to this explainer. Today we're going on a bit of a sci-fi journey. We'll travel straight down to the atomic level, and then bring it all the way back up to the smartphone screen you're probably looking at right now. We are decoding the completely fascinating physics of semiconductors.
Okay, so here is our roadmap for today. We'll start with the energy band concept, then define conductors, insulators, and semiconductors. Third, we'll look at intrinsic and extrinsic doping, followed by the p-n junction. Then, forward and reverse bias, and finally, how all this builds modern technology.
All right, let's jump right into section 1, the energy band concept. To really get this, we've got to introduce the star of our show, the electron. Navigating this rigid, crystalline atomic world, the electron's ability to move is actually what creates electricity. But here's the catch. Electrons can't just wander wherever they want. In a solid crystal, they live in very distinct energy zones. Think of the valence band like the ground floor where electrons are tightly bound to their atoms. They're essentially stuck there. Above that is the conduction band, which is like a free-flowing highway where electrons can easily zip around and carry an electrical current. But right between them lies a physical chasm called the forbidden gap, or the band gap. And the wild part? According to quantum mechanics, absolutely no electron can exist in this empty interval. They literally have to find enough energy to leap entirely across it.
Okay, let's dive into this a little deeper. If you look at an isolated, single atom, its electrons have very specific, discrete energy levels. But as atoms pack closely together to form a crystal lattice, those individual energy states actually overlap and merge. They broaden out into continuous energy bands. You got the conduction band on top and the valence band on the bottom with that critical forbidden energy gap sitting right there in the middle. And it's actually the physical spacing between the atoms that dictates exactly how wide this gap is. Moving on to section 2, conductors, insulators, and semiconductors. So how does this build our understanding of the physical world? Well, we can actually categorize every solid material on Earth based entirely on the size of that forbidden gap. It's kind of like a bridge. In a conductor, like copper or gold, the valence and conduction bands actually overlap. The bridge is completely connected, the gap is zero, and electrons just flow effortlessly. Now, for an insulator like glass or plastic, that forbidden gap is a massive, uncrossable chasm, typically greater than 3 electron volts. At room temperature, electrons simply do not have the energy to cross it. But right in the middle, that's our sweet spot, the semiconductor. It has a tiny band gap of less than 2 electron volts. With just a little push of thermal or electrical energy, electrons can easily cross that bridge.
Let's put some hard numbers to this. Take silicon, for example, which is basically the undisputed king of the semiconductor world. Pure intrinsic silicon has a band gap of exactly 1.1 electron volts at room temperature. And this isn't just a random number. It is the absolute perfect engineering sweet spot. It means silicon acts like a stubborn insulator at absolute zero, but at room temperature it conducts just enough to be manipulated by us.
Next up, section 3, doping, specifically intrinsic and extrinsic. Here's the thing though, pure silicon on its own, it's actually not incredibly useful for making computer chips. We have to transform it from a chemically pure, intrinsic material into an extrinsic powerhouse. And we do this through a process called doping. Doping is just the intentional introduction of tiny amounts of impurities to drastically change how the material behaves electrically. There are 2 main flavors here. For an N-type semiconductor, we add a pentavalent impurity, meaning an atom with 5 valence electrons, like phosphorus. For a P-type semiconductor, we add a trivalent impurity, an atom with only 3 valence electrons, like boron. Doing this totally flips the script on what carries the electric charge. If we zoom way down to the atomic level, when we inject phosphorus into the silicon lattice, something incredible happens. Because phosphorus has 5 outer electrons, but only needs 4 to bond with silicon, it ends up with 1 extra, loosely bound electron just floating around. This creates an N-type material where those negative electrons are the majority carrier. On the flip side, if we inject boron, which only has 3 outer electrons, it desperately wants to form a 4th bond. This leaves a vacant spot, a physical void that we call a hole. This creates a P-type material where these positive holes become the majority carrier. And this brilliantly illustrates how we alter the material's underlying physics. Specifically, it shifts the Fermi level, which is basically the probability of where electrons are hanging out. In an N-type material, all those extra donor electrons shift the Fermi level way up, right next to the conduction band.
But in a p-type material, the abundance of holes shifts the Fermi level down, right near the valence band. By just adding a few impurities, we've fundamentally reprogrammed how easily the material conducts.
All right, moving to section 4, the p-n junction.
So picture this. We've got n-type materials packed with extra free electrons, and p-type materials packed with electron-hungry holes. What happens if we seamlessly slap them together? Well, this is where the magic happens. Step 1. The materials join. Step 2. Because nature absolutely hates an imbalance, carriers start to diffuse. The crowded electrons from the n side rush over to the p side, and the holes from the p side rush to the n side. But as they cross the border, they crash into each other and annihilate. This creates step 3, the depletion region. It literally builds an invisible force field, an area completely stripped of free charge carriers, leaving behind a built-in electric field that acts as a solid barrier, stopping any further traffic from crossing over.
Now, when these electrons in holes meet up and annihilate, we call that recombination. Interestingly enough, it doesn't always happen in one clean, perfect jump. According to the Shockley-Reed-Hall theory, impurities or little crystal defects create what are called trap states right in the middle of our forbidden band gap. So an electron from the conduction band falls into one of these traps first, and then a hole comes along and is captured by that same trap, completing the recombination in 2 separate steps. Which brings us to section 5, forward and reverse bias. Now that we have this established junction with its own built-in depletion force field, we can actually exert external control over it. I want you to think about this for a second. What actually happens when you hook up a battery to this microscopic junction? How does that external voltage interact with the natural, built-in depletion force field we just talked about?
So the crucial point is, it's all about direction. In what we call forward bias, we connect the positive terminal to the p side and the negative to the n side. This actively pushes carriers toward the junction, shrinking that depletion barrier down until it practically vanishes, throwing the gates wide open for current to flow freely. But if we flip the battery, a setup called reverse bias, we pull those carriers away from the junction. The depletion region widens out, acting as a massive roadblock. Current is completely blocked, well, at least until we push the voltage so incredibly high that the atomic bonds violently break in what's known as an avalanche or Zener breakdown.
Finally, section 6, building modern technology.
Let's zoom back out from the microscopic physics to the real-world payoff that surrounds us every single day. Because everything we just discussed, it is the absolute foundation of modern civilization. When you put a p-n junction in a circuit, it acts as a diode, a one-way valve for electricity that converts your wall's AC power to your device's DC power. Stack 3 layers together and you get a transistor, the fundamental switch doing the math inside your computer's integrated circuits. When electrons and holes recombine and release their energy as light, boom, you've got an LED. And if you run that exact process in reverse, letting light hit the junction to knock electrons free and generate power, you have a solar cell.
It's honestly pretty breathtaking when you put it all together. Every single tap on your smartphone, every search you run, every video you stream is ultimately just the highly controlled, incredibly rapid, microscopic movement of particles hopping back and forth across a 1.1 electron-volt gap in a tiny piece of doped silicon. The next time you look down at your screen, just ask yourself, isn't it amazing that we've harnessed the quantum architecture of the universe just to send a text message? Thanks so much for joining me today on this explainer. I hope you learned something new.